Hello everybody, this is Mr. Woodward. In this video, I'm going to talk about how the big three kinematic equations can be applied to rising and falling objects. So let's take a look at this introduction together. When an object is in free fall, this is a key word, technical term in physics. The only force acting on it is gravity, and it accelerates downward at negative 9.8 meters per second squared. This is true whether the object is rising or falling. When it's rising, the negative acceleration causes the object to slow down, right? Because it's rising against gravity. When it's falling, the negative acceleration causes the object to speed up because it's falling with gravity. We can use the big three kinematic equations to help us solve problems involving rising and falling objects like this. So here's our big three below. Equation 1 looks just like it would have in the horizontal direction, except we're using delta y now, right? Because we're thinking vertically. And we have these vertical subscripts, sub y. And then we'll see that in equation 2 and in equation 3, right? We're in the vertical direction. So here at equation 1, it says, this equation relates to the vertical distance an object will travel to its initial velocity and acceleration. If the object starts from rest, then the initial velocity is 0. If the object is in free fall, then a equals negative 9.8 meters per second squared. So we're going to see that's true for freely falling objects. All of these values in all three equations, that should actually be a sub y, is going to be negative 9.8 meters per second squared. We're just going to assume that something is in perfect free fall, right? No air resistance. So let's take a look at how we can use these three equations to help us solve some problems involving falling or rising and then falling under the influence of gravity. Here's the first example. A tourist accidentally drops her camera off the Golden Gate Bridge and it hits the water below after 6 seconds of free fall. How far has her camera traveled just before hitting the water, and how fast does her camera travel just before hitting the water? So we got to imagine here's our Golden Gate Bridge going over the water below. Here's the two towers. And here's the water, right? And somebody drops their camera off the top. So the camera is maybe here, and then it falls bloop below into the water, splashes down, okay? So how far has our camera just before hitting the water? So in this first question, we want to know this distance, right? Delta y. So let's list out some givens, first of all, and see if we can answer this question. The first obvious given is the seconds, right? So we know that the time is 6 seconds. But then there's a couple of hidden givens. One is if you drop something, you're not throwing it, you're just releasing it from rest. So V initial is 0, and we're talking about in the vertical direction, right? And then this is a free fall situation. We're going to assume there's no air resistance. So we can say that the acceleration of this camera in the vertical direction is negative 9.8 meters per second squared. And then the unknown is delta y, right? So here we go. Let's try equation 1, which says that the change in vertical position is the initial vertical velocity times time plus 1/2 at squared. We know that the initial vertical velocity is 0. So even if we multiply that by the time of 6 seconds, and sure, I could actually throw in a 6 there, that's going to go away. Plus half the acceleration multiplied by the 6 seconds squared. So we end up getting negative 176.4 meters. And the negative means downwards, right? The camera is falling. So this means that you could actually figure out how high something is without measuring the distance, but by measuring the time that it takes something to fall from the top of that height. So you could climb to the top of a very tall tree and drop something from it, drop a baseball or something. And if you know the time, you could actually figure out how high that tree is. All right, let's continue. How fast does her camera travel just before hitting the water? So now we want to know the final velocity just before it hits the water. So we're going to go into equation 2. Final velocity is the initial velocity plus the acceleration times time. Okay, well, the initial velocity is 0. It's dropped. Plus 9.8 meters per second squared, and it's going to accelerate at that rate for 6 seconds. So it's just negative 9.8 times 6, which is negative 58.8 meters per second. And by the way, if you want to convert that to miles per hour, then this is just a rough estimate. You can double it. So this would hit the water at about 120 miles per hour. That would for sure be enough to damage the camera. In the next video, we'll look at example 2.